Hello, everyone. So today we're going to go through the step one, or the first part of the aldol condensation reaction, where we create and form the actual aldol. What is an aldol? Well, it can also be a ketol, right? If you use a ketone or you use two ketones, but when you use two aldehydes, you will be able to make an aldehyde alcohol. Okay, so let's first look at the aldehyde. It's really important to examine the aldehyde. We know that the aldehyde has a, has CH hydrogen bond. What's important is particularly the carbon adjacent to. We typically call this the alpha carbon, but on the alpha carbon, okay, they're adjacent. And when we call it alpha, it means that it is alpha to the carbonyl, which is that carbonyl carbon. But anyways, carbon on the terminal end is going to have that three hydrogens implied to it, unless otherwise it's going to be bonded to something else. But when we don't draw it, there's three hydrogens there still. But why do we particularly draw out this hydrogen in the first step of the aldol? Is that this hydrogen is going to play an important role of creating enolate. And enolates are really important in carbonyl chemistry due to their nucleophilic nature. Okay? So what we're going to do is going to do a deprotonation step first to form the enolate. I'm going to use hydroxide. And hydroxide is going to have that negative charge. And that negative charge on the oxygen wants to, get a hydrogen, proton. So when it does attack our alpha hydrogen, particularly right here, that proton is going to make or neutralize that negative charge on the hydroxide and make water. But what's important is that the electrons here, that bond is going to form that pi bond there connecting, and arrow push the carbonyl carbon. Can't have like five bonds on the carbon. So that carbonyl carbon connected to the oxygen is going to break and move its electrons up to the oxygen. Now oxygen is going to be on the carbonyl oxygen is going to become negatively charged due to the extra electron. So, of course, now when we did deprotonate, we will form that pi bond on this blue carbon, alpha carbon here. And of course, the other side's still that hydrogen, right? We didn't change anything. And that enolate, it's really important because it has that nucleophilic character where if we move the electrons back down and we use the electrons here, from the pi bond to go, we are able to go and attack something. And this is where our second carbonyl aldehyde is going to come in. And that carbonyl aldehyde still looks the same as the original thing that we deprotonated. We can, even draw it out to look like that, but it's not necessary because we're not going to deprotonate any alpha hydrogens. So that's why we don't draw it out, and it doesn't exactly look the same, but it's the same actual thing. And so remember that pi bond is going to go and attack this new aldehyde, second aldehyde's carbonyl carbon, who's electrophilic. Remember when we're talking about electrophicities of our carbonyl, the electrophilic carbon can get attacked, okay? And when it does, it will move its electrons up and break that electrons up to the oxygen. And this actual step, it's called nucleophilic addition. It's going to allow us to create kind of the molecule all together, these two add them together pretty much, right? And so when we add them together, I'm going to draw it in a way where it still retains who's who, because a major point of confusion for many students is who was the enolate, and on the structure, who was the new aldehyde part. Okay, so Now this is what's been important. When we do that attack here, we're going to create a new bond. So I'm going to draw the new bond in red, just to show y'all. But there's that carbonyl carbon. Okay. And since the electrons moved up to the oxygen, it's broken. The pi bond gets broken, and then it moves the electrons to create that negative charge on the oxygen of the new carbonyl, the second carbonyl. And you might ask, okay, well, Emily, like, what happened to our fellow friend, Mr. Hydrogen over here? Well, he's still there. And in my mind, I like to think about the hydrogen just kind of moving like to this, like kind of like moving around, like moving to make space for that attack to happen to create that new bond. So, but what is important is that we need to remember on this side, there's still carbon there. So that for sure needs to be notated. But, obviously to make your life easier to remember, like the hydrogen's still there, it didn't disappear. You can draw the hydrogen right there. Um, so now what's important is that we're just, we've created we're almost there. We just need to come up with a protonation step with some acid to protonate that particular negatively charged oxygen right there. And then we create our desired product, the aldol. Let's actually go into naming. On this structure, who is the highest priority in terms of naming? Right? We can tell by two functional groups. There's an alcohol and there's an aldehyde. Well, aldehydes, carbonyls in general, are higher priority than alcohol. So we know that the name is going to end in the ANAL aldehyde ending. Or if you used a ketone or two ketones, you can end in the ONE. But for this particular structure, when we know that this is the highest priority, we're going to be able to start numbering our carbons from the carbonyl. Let's think about it. It's going to be called butanol because there's four carbons total. And then we notice that on the third carbon in general, that we have that alcohol functional group. So we're going to draw a right 3-hydroxy butanol. And so that's how we name that. And come back later for the second step. Thank you.